from here.
Here, take one pass.
Oh, great. Thank you.
I didn't bring any books, I didn't bring any catalogs, so at least to get the business cards to pass around. Everything's on the website.
We need more cards.
More?
They're not being passed.
I think there's more coming this way.
Yeah.
Pass them all the way down, please. Yeah. There. Where's mine? You didn't give me one. I didn't say what you need. I didn't give it up.
Well, there you go,
Okay.
I saved
This is
one
the
just
last
in
one?
case. I got a few more.
Oh, good.
Okay, I'm glad to be here. I'm happy to present this short summary of an ongoing research project. This was previously presented about 4 years ago at the Vigier Conference, just specifically on axial magnets. So I'll review that part of it as well as the advancement into the radial magnets as well. Oops. I will see. I met Vigier in 2002 at the Swiss Weinfelden Conference, and what's interesting about that particular presentation of his is that he published it as the 400% excess energy produced from lithium. And it was a pretty provocative topic, and also very interesting that he was also supporting a new source of energy. And that was the focus of that particular conference. What we're concentrating on today is the concept of gradients being the source of energy that we use traditionally in our society. The thermal gradient, for example, the voltage gradient, gravity gradient, pressure gradient, those are all pretty familiar to us, and definitions are on the screen. What we don't see in everyday use is the magnetic gradient. And magnetic gradient has often been denied the reality of existence for any accessible energy. However, you see in physics experiments that it actually is useful. For example, it's also called an inhomogeneous magnetic field, and it's specifically known to most of us who are physicists as the Stern-Gerlach experiment. And you see an example right here where we have a triangular magnet above a rectangular magnet, which creates a pointed magnetic field, which is basically inhomogeneous. And what the advantage of such a field is that then you can apply, or you are producing, a unidirectional force. And this is quite unique in terms of arrangements of magnets, as we know from all the hundreds of years or a couple of hundred years of using various magnetic motors. We also see in the Hartmann patent, which is 4215330, the advantage of using such an increasing magnetic field specifically for producing a force on a steel ball. And that's exactly the experiment that's featured here above a 10-degree incline. So this is a very good implementation of the application of a magnetic field gradient. And the equation for this use is described at the bottom, just from Schoen's outline series, modern physics. Specifically, it's the magnetic moment times the derivative of the magnetic field in z direction. And so what I did over the years, and this has been quite a long journey for a couple decades of researching the 1979 article, for example, and the subsequent patents from the Popular Science Magnetic Wankel article by Kure-Takeo. Kure-Takeo is a Japanese firm, or was a Japanese firm back then, that patented a number of various spiral magnetic field motors that they we're intending to implement in electric cars. The basic problem, of course, is that it's being driven by an electric coil, and the actuator will tend to deny or cancel out any advantage, mechanical advantage that we would hope to gain from the entire cycle being driven by permanent magnets. So this has continued even to recent years, where Paul Sprain ended up patenting one more version of the Kirill motor and essentially not producing anything useful. Well, the interesting thing, of course, is that the equations for the circular implementation and the linear implementation are virtually the same, and that's the important physics behind it. So now we look at the spiral magnetic motor itself. These are a number of different models that I built, and the Archimedean spiral is actually a very easy one to obtain the equation for, since it's a linear one dependent on theta. And it's actually very nicely drawn in the software that's available online to essentially make sure that you're putting, in my case, permanent neodymium magnets exactly where they belong. So it creates a constant torque for more than 75. It's actually around 90%. 88 is the correct number. 88% of the cycle, essentially driven by permanent magnets. So I ended up applying a little spring latch to look at the maximum distance that any of these motors could achieve. And these were some of the suggestions. This was done by a Norwegian fellow saying, well, if you had a whole bunch of them gang together on the same axis, perhaps it would smooth out the operation, much like a 8-cylinder motor tends to do in a gasoline engine. So that's essentially how I got to trying various numbers of magnets, even up to 6 magnets on a rotor. It doesn't really give you much of an advantage. Even the mirror image impacting spiral motor, which was very cumbersome to try to build, a spiral going the opposite way as the one at the bottom, and trying to exchange energy between them. Of course, there were some losses and still no advantage. And essentially, as you review the governing equations for this, we're looking at the change of the magnetic field in the theta direction. So if we maximize the radial magnetic field, or VR, you tend to get more of a change per degree. And that is actually the goal, is to achieve maximum torque. Well, as an aside, I threw in this extra part of the slide here, which is really unrelated, but it gives you a comparison, which I was very impressed with from a journal article that tried to convey to the public that magnetic fields essentially have 50,000 times the amount of energy stored in any cubic meter than an electric field does. And the way they arrived at that conclusion is, well, just try to conceive of a maximum magnetic field. Well, a couple Tesla is a good number. You can go down, actually, and still get a very remarkable comparison. But 2 Tesla is pretty difficult to produce in the laboratory. I know I've tried. 1 Tesla is almost impossible, even with the most powerful magnets that are commercially available. And of course, if we look at 3 million volts per meter, that also is pretty difficult to achieve and maintain without having a short circuit across air. We're doing both of these in air. And using the both potential energy equations to come up with the numbers, you end up with 40 joules per cubic meter for the electric field, but you end up with 2 megajoules per cubic meter for the magnetic field. So the electric field is essentially 50,000 times smaller than the equivalent magnetic field for the same cubic meter. So it gives you a little bit of motivation to go a little bit further and perhaps someday looking at the advantage that magnetic gradients offer because of the potential stored energy. So what I show here is the 5 different rotor sizes and also the information about the strength of the magnets, both on the rotor and the stator. So these are all the different sizes from 1 inch up to 10 inch size rotors. Some of them are pictured here, and also the kilogauss strength versus each one. As you can see, as I got to larger disc sizes, I was able to stack a few very large and expensive neodymiums for the single rotor magnet. And what we learned from that is that one thing I forgot to mention is that the plexiglass arrangement here are phototransistors. So I was able to computerize the data acquisition of the rotation, the accelerated rotation of one cycle. And so here's the composite angular velocity result for all the different disks that were just shown. And you can see that, surprisingly, for example, the 3-inch rotor seems to have actually achieved even the limit of the data acquisition system that I had. So that was an unusual finding, and I didn't expect to see the 3-inch rotor to be more powerful than, say, the 10-inch, which had stronger magnets. Here's the information about the latch point, and that specifically is the, you'll see it on the next graph, the maximum permanent magnet powered rotation. Now, one thing I was curious about too is what is the actual force that the rotor is being providing or generating with the rotation. And measuring back torque is, of course, an important issue. So this is essentially the experimental setup with a linear scale to do so. It's calibrated. And here's the composite data result for the calculated back torque, kinetic energy, and also the measured rotor mass and rotor magnetic field. The 10-inch rotor actually has the highest kinetic energy, as can be seen on the purple graph at the very front. The important part is that the rotor diameters are here, so as we go back just on the 10-inch line, we can see the measured back torque, the rotor mass, and also the magnetic field. So, interestingly enough, the rotor magnetic field tended to be sort of in the same range of 0.4 to 0.8, but the obviously the back torque and the rotor mass tends to be exponentially related to the size. I was mostly interested in the amount of kinetic energy that was being produced, because I'm convinced that as you have a tremendous amount of momentum, which is what the 10-inch rotor provides, and of course we can go to even bigger ones, which I'm looking forward to in the next round, we essentially can envision borrowing, say, 2% of that energy. And 2% is enough to do energy harvesting with most of the triggering and switching mechanisms, which I'll show in a couple seconds here. One other graph which I found interesting was to actually plot the rotor potential energy versus displacement. And that's what we see at the top here. And we basically get a curve that was the critical one for identifying the 315 degrees over 360. The angular displacement, also the rotor torque, which I diligently measured for all of these data points, essentially gets to this maximum amount at the 315 point as well. So essentially we can then see where the half a joule energy comes from, which is obviously less than 0.8 joules of kinetic energy. And to me, this was a favorable comparison. How can we actually see a higher kinetic energy being produced than the positive work required to maintain that latch point, which is the maximum rotor torque required. So I was encouraged to continue. Now, since Lathwaite is a popular fellow in this circle, it might be interesting for you to know that Professor Lathwaite also has a suggestion for improving the performance of this And as you can see, the north-south magnet that he's providing is very close to what we're using and could be the rotor in question if we essentially used a bar magnet design instead of a vertical magnet as you see here. But the important discovery that he describes is the concept of induced opposite poles, or in other words, Lenz's law being applied in a favorable fashion. And this is what he calls favorable hysteresis currents. And I found this so attractive that I then researched it in various textbooks, and I found one particular one by J. Wiley and Sons called Ferromagnetism, 2003 textbook by Bosworth, who actually came up with the equation to describe the creation of the growth, in other words, of eddy currents for the various speed of rotation. And this is exactly what I was looking for. So I was pleased to enhance Lathwaite's prediction that this is actually possible. And what's interesting is that the equation actually predicts 1 centimeter thick aluminum or copper plate, and essentially the relative slow buildup over 1/10 of a second is very favorable for the slow speed of rotation that we have for the motor. And so that's the next stage of development if I was going to pursue this axial design. One other interesting discovery that I carried in sort of the folder that I used for this is the Huygens wire based on the Barkhausen avalanche magnetic domains. To me, this was also a very interesting phenomenon because this is a bistable bicolloid metal with 2 different permeabilities in one wire. And what this has been used for in commercial applications is the electronic ignition. And that's exactly how we've been firing the spark plugs in our cars for years, thanks to Huygens wires. So we also find them in hotel doors. As you slide your card into a hotel door to open it, there's no batteries in that door handle. Essentially, we're relying upon the movement of the magnetic strip in the hotel key to activate the Huygens avalanche. And this is a magnetic pulse that's being produced at a very favorable amount of energy. In fact, the signal-to-noise ratio actually is the consideration that we talk about. And in fact, the pulse amplitude is in volts instead of millivolts for any other comparable mode. So I was encouraged to consider that as one switching mode with a more robust design of Huygens rod instead of just wires. Now, another collaboration that I've now started and re-energized is with Dr. Wuno. Radial design. Radial design will actually be more developed in the paper that's due in January. But I thought I'd give you some slides of the prototype that I'm working on right now. What is very interesting about this, you see the setup for the axial design in back. The radial design has 2 tracks. You can see one of the operating modes on the internet, which of course the internet often has videos of almost everything working by themselves. But here we actually acknowledge the fact that you need a good, well-designed stator that can actually move slightly, very slightly back and forth at the right moment. And if I brought the apparatus with me, it's fascinating to watch how very slight amount of movement is needed for this stator magnet to activate the switching point. And of course, the switching point is right here as the force increases with every rotation. So the conclusion is that spiral magnetic motor designs now provide almost 90% of a permanent magnet motor powered cycle. Actuation is needed for the switching field in the last 10%. And many energy harvesting means are now available, which have only emerged in the past 10 years to make this a long sought after goal. And hopefully achievable in our lifetime, that we'll see magnetic motors that essentially are run through energy harvesting means, even if we use ambient solar power, which now is also available. But I want to reserve that to the last resort because I believe that we can actually take advantage of stealing just a little bit, much as we do in our gasoline-powered cars. We steal a little bit of the energy for recharging battery and so forth. And the details will be provided. And I even made it before the time limit. Wow. Any questions?
Any questions for Tom?
Elizabeth, what do you think?
I think it's very interesting.
Anybody else working on this?
I really want to look into it more. I'm trying to get set up to do my plasma physics experiment, so I need to keep in touch with you about proceedings and how you're proceeding, but very interesting.
Thanks.
Very good.
Amen.
I guess my question would be, I see things like piezoelectricity, the Seebeck and Peltier effects, but then you'll have the back EMF and how really, that's really the bucking field that produces the resistance to a working of a magnetic motor.
Well, back torque really is.
Yeah,
there's
back
no
torque.
EMF
It's a
involved.
back torque. Yeah, you call it back torque, I call it hysteresis. You had a hysteresis curve
Well,
up there.
favorable hysteresis looks exciting, and
But I think
look
there's
forward to
another
reporting
way
that.
of kickstarting using the hysteresis in a positive sense in some work I did with my late husband, Bill Van Bice.
you did work on that already.
Oh, yeah, but it has to do with setting up the proper waveform. There's a complex, actually it's a ringing square wave, but it has to do with the formulation of soliton physics. And that's in one of my earlier patents. So there's a whole bunch of thinking I have about that.
Elizabeth has several intriguing patents, that's for sure.
Yeah.
Anybody else? Yeah.
What is the principle? You switch on one magnet at, like a regular motor, or, I mean, what's driving what?
Oh, well, essentially, you've got permanent magnets in a spiral.
Yeah.
Either, as I call them, axial magnets because they're in the axial direction, or else with the V-track, they're in the radial direction around the rotor itself. And all it needs is basically the setup is started advantageously, say, at one end of the spiral, and either in the attractive mode or the repulsive mode. So you're letting it go. In other words, you set it up at the very start of the spiral, and you let it go, and you see it go through one cycle. It'll stop by itself and retract to an equilibrium point. So that's one cycle by nature that always has stopped everyone cold.
In my mind, I want to imagine that you have something like brushes in there, and you turn one of the magnets on and off. No.
Now, you could, and then you make the mistake, as historically has been made by Curteco and all the rest since then, that you're now putting electrical energy in, trying to minimize the amount of external input to get some maximum mechanical force out, but it always equals everything.
I got a question.
Equals out.
On the Faraday disc, when you put the brushes on the disc and the axle.
That's
so
an
you're running
unrelated question, though, Elizabeth. I got to talk to you about it afterwards.
Well,
That's another
my
whole book, another
question
title.
is, what causes that apparent anomalous current?
As I say, that's the homopolar generator. I wrote a whole book about it. I'll be glad to discuss it
Okay,
afterwards.
okay, you can't.
Spiral magnetic motor is the topic at hand here.
Okay,
Did
sure.
you have another follow-up question there?
No.
Okay, excellent.
Using your best rough estimation, even if you don't believe in crystal ball, how far do you think you are from a commercial rough image unit that I can buy? How long do I have to wait?
How long do we have to wait is the question. I would give it maybe 10 years, 5 years at the least. I'm going to retire next year, guaranteed. I've been trying to do the early retirement from the government job I have, but it looks like it'll be, within the next year. So then full-time into this project and a couple others, but this is my major new baby that I've spent a lot of time on already. So, and this is actually very attractive to the few other professors I found who are also magnetics experts. And especially Dr. Uno, who's already done magnetic switching. So. Last question, anybody? No? What's that? Thank you.
We have been a little tardy and lax